Let's introduce the concept of a Riemann sum, or computing the area under a curve. Remember that these videos are to be viewed after you've done the reading in your book so that you're at least a little familiar with the terms. So if we have a curve that's very simple, let's just see this function, this not very curvy function, which is a line, and we wanted to know the area under that curve. It'd be really easy to figure out what the area under that curve is over the interval from A to B. We could just partition this guy up into geometric figures with easy to compute areas. Like here, it would be B minus A, and then whatever this height was, you could just do area of a rectangle for that portion. And then for this portion right here, you could compute the area of a triangle, right, which is 1/2 base times height. So you need to figure out the length of the base and then the height. But then you've got length times width, 1/2 base times height. Add those two up, you've got the area under that curve. And that gives you the area under the entire curve defined by the linear function f. But a complication arises when we have functions that are not linear. Like, let's just say, for example, this one. I'll fake a function. Say here's the function f now. And we want to know the area under the curve on the x-axis interval from A to B. Well, we can't divide that guy up into geometric figures with easy to compute areas. So what we'll do is we'll divide it up, divide the interval up into subintervals. Let's do 4. So it's 1, 2, 3, 4 subintervals. And then we'll chop that area under the curve up. Here's the area that we're looking for. This entire area under the curve. Chop that area up into geometric figures that we can compute the area of. And what I'll do is I'll go up and I'll define some rectangles that are defined by the right-hand endpoint of each of these little subintervals. The height is going to be defined by the right-hand endpoint of each of these little subintervals. So maybe I have here a rectangle whose height is defined by this right endpoint, and I can easily compute the area of that rectangle. I see that I'm over-counting. There's some area here that's actually not under the curve. I'm over-counting it. Now I'll come over here, and again, using the right-hand endpoint, define the height of my rectangle. I'm doing some over-counting. This is area not under the curve, but I'm also doing some under-counting. I'm not counting this area under the curve. Go to the next right-hand endpoint, define the height of my rectangle, and the last one, define the height of my rectangle. I'm counting too much, so in general, I think this one's going to be an overestimate, but if I add up all these areas under the, add up the areas of the rectangles, oops, and I get an estimate. Or an approximation of the area under the curve. And so in calculus, we do a lot of limiting. And so we ask ourselves, well, what could I do to get a better approximation? Because obviously this one's crummy. I've overcounted here, here, I've overcounted here, I've under and overcounted on this interval. If I had more rectangles, if I had a finer partition of rectangles to cover the area under this curve, I could get a better approximation. And so that's what we're going to do. We're going to come up with an expression that writes the sum of n rectangles, the areas of n rectangles under the curve, and then we'll limit as n goes to infinity. Let's work an example of an approximation in the next video.